When one begins to learn about the subject of astrophysics, it doesn't take very long before the term, the Doppler effect, gets brought up and thrown around. It shows up in conversations and discussions about everything from the motions of stars relative to the sun to the expansion of the universe. But what is this phenomenon? How does the Doppler effect occur, and how can it be used to learn things about the behavior of physical systems, especially those kinds of systems studied in astronomy and astrophysics? In this episode of the Scientific Odyssey, we'll pause our journey into the ever deeper reaches of the cosmos to equip ourselves with a tool that will allow us to gather even more information from the light that reaches us from the furthest distances our telescopes can see. We'll also take some time to consider many of the instances where the Doppler effect has been used to pry open nature's secrets and allow us to peer inside what was once unknown. Once we've done this, we'll be better able to meet the challenges that await us on our journey. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 35.1, Supplemental-The Doppler Effect. In times past, when voyages of discovery were to venture into new realms and uncharted waters, they would stop at a port to pick up an expert guide or acquire a piece of equipment that would aid them in their navigation. This is what we'll be doing this week. While we've given a brief explanation of the Doppler effect and kind of a little bit about how it works, it seems to me that we could use a bit more time to talk about the idea, how it was arrived at, and how it's used. Once we've done this, we can head back out into deep waters to continue our journey of discovery, better equipped to understand the ideas we encounter there and how they're used. So, to give a brief definition of the Doppler effect, it is the perceived change in the wavelength or frequency of a wave phenomenon due to the relative motion of the source of the wave and its observer. With that said, though, there's a lot to unpack about this in order to get a full understanding of what that definition actually means. To do this, we need to start with the question, what is a wave? Well, a wave is a way nature moves energy from one point to another without moving matter that entire distance between the 2 points. To better understand this, it'll be helpful to have an example in mind as we work through these concepts. In your mind's eye, imagine a perfectly still body of water, say a pond at the dawn of a cool spring morning. Maybe you've been sitting at its edge after a night of watching the expanse of the sky turn around Polaris, or looking at the Southern Cross wheel around Polaris's opposite point if you're in the Southern Hemisphere. As you wait for the sun to rise, you pick up a small rock from the edge of the water and you throw it into the center of the pond. When the rock hits the surface of the water, it transmits a significant portion of its energy of motion, or kinetic energy, into the water at the impact site. Now, what this energy will do is travel away from that impact site in a circular pattern. Can you see that in your mind? Now, what's interesting is that it's not actually the water directly from the impact site that's going to travel across the pond. That's more or less going to stay in the same place. Instead, what you'll see is the energy travel outward from the impact point through the water disturbing the surface of the water from being perfectly flat, what is known as equilibrium. This disturbance will be up and down a small amount in relation to the amount of energy being moved through the water. Again, you can imagine a crest of water, say a couple of centimeters wide, with a bit of a trough on either side, moving away from the place where the rock dropped into the water at some speed. Maybe we'll say that the circle gets 5 centimeters bigger in every direction per second. This disturbance is called a wave. Specifically, the kind of disturbance we're talking about is called a transverse wave, since the displacement of the medium is perpendicular, or at right angles, to the direction the wave is traveling through the medium. In other words, the displacement of the medium, the water's surface, is up and down, while the wave travels perpendicular to that outwards. There are other kinds of waves. One is known as a longitudinal wave, where the medium is disturbed parallel to the direction of the wave travel. Sound works like this. If you think of clapping your hands once, you compress the air right where your hands meet, increasing the air's density there. On either side of the compressed higher density region, there is a lower density area of rarefied air. This disturbance will travel outward from your hand with the air being compressed or spread out in the same direction as the wave travels. Now, there can also be torsional waves where the medium is twisted, or what are known as love waves, where there's sort of a rotational component to the wave motion. If you've ever stood on the edge of the beach at the ocean and you watch the sand particles in the ocean water just at the edge of the beach where the waves breaks, you'll see that rotational motion in the motion of the sand particles. Now, to get back to our example, as our water wave travels outwards, it's not the water from the center of that impact that's moving, it's the energy. As the energy passes through the water at some point, a distance away from that center, it disturbs the medium, the water, for a moment, causing it to go up and down before passing the point by. As the energy spreads out, it is dispersed, so there's less of it per part of the overall wave, and so the up and down motion of the water will get smaller and smaller. Also, due to viscosity effects in the water, that wave crest will spread out a little bit as it travels. Of course, if you live in a place where you have access to a quiet pond or pool, you can go out and test these observations for yourself, which is, of course, what our old friend Francis Bacon would tell you to do. Finally, as our wave reaches the shore, the energy it transmits to that place where it lands can then do work on something there. On a very large scale, if you're clever, you can engineer things that can capture that energy being transmitted by large, say, ocean waves and transform it into electrical energy. But that's a story for another day. So far, so good. What we've been talking about here is a single wave generated by a single event. Now, let's complicate things a little bit. Let's say that instead of picking up one rock, you picked up 10. And let's also say that you threw one of those rocks every 2 seconds. And because you're an awesome shot, you're like the world rock throwing champion, each of the rocks lands in the same spot on the pond. If you could do this, you'd then produce 10 wave crests, each traveling outward 2 seconds after the previous one. This would be what we call a periodic wave, since the same wave crest repeats over and over again, traveling away from that impact point. Now, let's add something to this. Let's say you were to also imagine that at some distance away from that center impact point, there were a ladybug being taken on a boating date by an admiring gentleman bug, and the two of them would be sitting, let's say, on the pond in a small boat made from a leaf. If you had something like that, they would measure the crests of the wave as occurring 2 seconds apart as those crests traveled past them. That is, of course, assuming that the lady and gentleman bugs carry watches with them as their lovely leaf boat bobs up and down. If you looked at the 10 waves you'd created, you'd notice that there was a distance between the wave crests. This distance is called, rather sensibly, the wavelength of the periodic wave, and it would depend on how often you threw the stones, i.e. the number of stones per second or frequency of the stones being thrown, as well as how fast the wave traveled through the water. The faster the wave traveled, the longer the wavelength would be. And the more often you threw stones, or the higher the frequency, the shorter the wavelength would be. In this, the frequency is the inverse of the amount of time between wave crests. That's something we call the period, by the way. If the period is 2 seconds, as in our thrown rock example, the frequency would be the inverse, or 1 wave cycle every 2 seconds, or half a cycle per second. The shorthand name for a cycle per second is called a hertz. If you had been really good and, say, thrown a rock every half a second, your frequency would have been 2 rocks per second, or 2 hertz. Every single type of wave can be characterized in this way. Let's think of sound, for example. If you were to hear a pure tone note of, say, that A below middle C, what you would be hearing would be the longitude pressure wave moving through the air with 220 wave crests, or pressure maxima, passing by your head every second. That's its frequency. The pitch of a sound is our way of perceiving the frequency of that specific type of wave that we call a sound wave. Now, if you were to then hear an A an octave higher than that, it would have twice the frequency at 440 hertz, which means that the wavelength of the higher A note would be half the distance as it was for that lower A note, because the frequency of a wave and its wavelength are inversely related if the wave travels at the same speed through the medium, which we're assuming here since both waves are sound waves. As a bit of trivia, the speed of sound through air in typical temperature, humidity, and pressure conditions is about 340 meters per second, or about 1,100 feet per second. This means that the wavelength of a 220 hertz A note is just a bit over 1.5 meters long. Since Thomas Young showed that light was a wave in 1801, we can apply this same type of analysis to light. Unlike sound, however, light doesn't require what we typically think of as a physical medium to propagate through. Light is a wave in the electromagnetic field, as was shown by James Clerk Maxwell in the 1860s. Another major difference between sound and light waves is that light is transverse as a wave, like water waves are, rather than being longitudinal the way sound is. Finally, a third difference is that light has a much greater speed, about 1,000,000 times faster at 300 million meters per second, or 186,000 miles per hour. For visible light, say for the color yellow, the wavelength of the electromagnetic wave is about 550 nanometers, or 550 times 10 to the negative 9 meters long, a very, very short distance. This means that the frequency is about 500 terahertz, or 5 times 10 to the 14 hertz. As a comparison, for the visible portion of the electromagnetic spectrum, violet light has a wavelength of about 400 nanometers, while red light has a wavelength of about 700 nanometers. So blue light has higher frequency than red light. When you talk about your favorite, say, FM radio station being at around 100 megahertz on the dial, that means that it has a frequency of 100 times 10 to the 6th hertz and a wavelength of right around 3 meters or 10 feet in length. Radio waves are, when compared to visible light, very long wavelength, low frequency forms of electromagnetic waves. The key thing to take away from these examples is that the higher the frequency a wave has, the shorter its wavelength will be, and vice versa, for that type of wave's given speed. Anything that acts like a periodic wave behaves in this way. This is going to be important to understand as we add some complications to this picture here in a minute. For now, though, let's take a quick break to let our brains cool off a little bit. Okay, so now it's time to get into those things that will allow us to better understand what's going on with this Doppler effect. To start out, let's go back to our pond and think again about how our gentleman and ladybug are experiencing or perceiving the periodic wave being created by our rock throwing. If they're sitting in one place, after they wait a bit for the wave crest to travel from the place where the rocks hit the water to their boat, they will bob up and down at the same rate or frequency as the frequency with which we threw our rocks. Great. If they now know the speed of the water waves, then they would be able to take the frequency and that speed and calculate the wavelength in the same way we were doing there a little bit before the music break. Let's say, though, that our small bug-sized boat has a small bug-sized outboard motor on it, and so our couple can motor along in the water as strikes their fancy. By the way, are you picturing the gentleman and ladybug in the same sort of Victorian-esque steampunk outfits I am? Her having kind of a cool parasol and him holding a retro-futuristic pocket watch like I am? No? Well, maybe it's just me then. So anyway, let's say that our dashing bug couple has pointed their boat towards where we are throwing our rocks and are traveling in that direction at a speed that is some reasonable fraction of the speed of the water waves that are now moving towards them. Because they are moving in the opposite direction of the waves, they will run into those wave crests more rapidly and bob up and down with a higher frequency than the frequency with which we threw the rocks. If, conversely, they were traveling away from the rock impact point and in the same direction as the waves travel, the wave crests would overtake them more slowly and they would bob up and down more slowly or with a lesser frequency. In the first case, they would then calculate a shorter wavelength, and in the second, they would calculate a longer one. This change in frequency due to the motion of the observer is one way in which the Doppler effect occurs. If the thing that emits the wave is stationary, but the observer is moving, the frequency of the observed wave will shift. The frequency will go up if the observer is moving towards the source, and it will go down if the observer is moving away from the source. If we change our wave system to sound, then what would change would be the pitch that we heard. If we're traveling towards a source of sound, the pitch would be higher since the frequency we perceive is higher. That 220 Hz A note might shift up to an A sharp or a B if we traveled fast enough. On the other hand, if we moved away from the source, the pitch would be lower. Light, since it's also a wave, will have the same thing occur. If we travel towards a source of light, the perceived frequency of the light will be higher and the wavelength will be shorter, and so the light will be shifted to the blue end of the spectrum. If we travel away from the source, the frequency will be lower, the wavelength will be longer, and the spectrum will be shifted towards the red side of the spectrum. While we won't break out the full calculation here, what should be understood is that the amount of shift has to do with the ratio of the speed of the observer to the speed of the wave. Therefore, with sound, to get something around a 10% shift in the frequency of the wave, you would have to be traveling about 10% the speed of sound, or around 35 meters per second, which is close to 75 miles an hour. To have an equivalent 10% in the shift of the specific frequency of light, you would have to be traveling 10% the speed of light, or about 30 million meters per second. Now, the great thing about this whole calculation and relationship is that if you know what the frequency of the wave should be, what the frequency of the wave you measure actually is, and what the speed of the wave should be, you can then calculate how fast you are moving towards or away from the source of the wave. In other words, let's say you're traveling along a road parallel to some train tracks when you pass a stopped train. Just after you pass, the train blows its horn at a frequency you know to be, say, 440 Hz. If you use the microphone on your cell phone to measure that frequency and you found it to be 419 Hz or 21 Hz lower, you could calculate that you were moving away from the train from about 5% of the speed of sound, or 17 meters per second. A similar type of calculation can be done with light. If you know that a specific absorption or emission line in a spectrum is supposed to happen at a specific frequency or wavelength, by calculating the shift in that line, you can determine if you are moving towards or away from the light and at what speed. So that's one way to Doppler shift the frequency of a wave. Have the observer move with respect to the source. The other way to create a shift is to have the source move with respect to the observer. This is maybe a bit harder to visualize with our pond example, as it's hard to imagine the rocks splashing into the water at both regular intervals and with even spacing, either moving towards or away from our bug couple's leaf boat. However, let's see if we can try. Imagine, if you will, that when you throw the rocks, your aim is so good that you can have the next rock splash into the water 2 centimeters closer to the boat than the previous rock. Now, if the wave crest from the first splash were to travel, say, 10 centimeters in the 2 seconds between the splash of the first rock and the splash of the second, then the wave crest will now only be 8 centimeters apart. When the waves get to the leaf boat, they will have a wavelength of only 8 centimeters, and thus the frequency will be higher than they would have been. The opposite will be true if you splash the rocks in the direction away from the boat. In that case, the wavelength will be 10 plus 2 centimeters, or 12 centimeters, and the frequency of bobbing up and down in our little boat will be lower. The same thing, of course, happens with sound. If you've ever sat at a railway crossing when a train blows its horn as it goes by, the pitch of the horn will be higher as the train approaches, and then will suddenly shift to being lower as the train passes your location and then moves away from you. If you could measure the size of the shift, you could calculate the speed of the train. As before, this also applies to light. If the light source moves towards your observing location, the frequency is blue shifted. If the source is moving away, it is red shifted. The amount of the shift will tell you the velocity of the source towards or away from the observer. Before we leave the theory, let me make just a couple more comments. If both the source of the wave and the observer are moving, then there's a version of the Doppler effect formula that takes both motions into account. This is how we can measure the velocity of a space probe, such as the New Horizons mission to Pluto and beyond, moving through space. The craft will continuously send out, in the direction of the Earth, a very accurate known frequency signal in the radio portion of the electromagnetic spectrum. The frequency of that signal is then monitored in real time by the large radio telescope dishes of the Deep Space Communications Network. By looking at the very small shift in the frequency of the signal and knowing the velocity of the Earth in its orbit around the Sun, the velocity of the spacecraft can be very accurately calculated. Of course, to do this correctly, it's absolutely vital to have a very accurate knowledge of just how fast the Earth is revolving around the Sun and rotating on its axis. And that's where all of the work by guys like Leverrier and later on Einstein are going to become so important. Also, if the wave is sent out from a stationary source, interacts with a moving object, and then returns to the source to have its frequency shift measured, the calculation actually has to be done twice. Once as if the observer is moving, and once as if the source is moving. And this is how a handheld radar gun works. It sends out a short pulse of electromagnetic waves in the radio part of the spectrum. The gun knows the frequency of the waves. It then waits to receive the reflected radio waves, and when they arrive, it measures their frequency. The software built into the hardware of the gun then does a calculation to find the speed of the thing the waves interacted with, whether that be a baseball thrown by the closer in the 9th inning of a close major league game, or a car that may or may not be driven in excess of the posted speed limit. As one final piece of this, you may be wondering why I keep using examples that involve radio waves when I discuss electromagnetic phenomenon. It turns out that the higher the frequency of a wave, the more energy is needed to produce it, and the more energy it transmits to whatever or whoever it interacts with on the other end of its travel. If you think of taking a garden hose and using your hand to create a transverse wave in the hose, to increase the frequency of the wave, it takes your hand a lot more work to do that. If you wiggle the hose slowly, not so hard. But if you really want to wiggle it back and forth quickly, that takes a lot of effort. So if you want to create a wave that doesn't require as much energy, you want to go with as low a frequency as possible. In the electromagnetic spectrum, that means radio waves, as they are the type of electromagnetic waves that have the lowest possible frequency. The flip side of this is that if you have a physical process in nature that produces waves, the more energy that process involves, the higher frequency waves it will produce. This is why when things get hotter, they produce light at shorter and shorter wavelengths with higher and higher frequencies. This is also why things like X-rays can be so bad for living organisms. X-rays are electromagnetic waves that have very high frequencies, higher than violet and ultraviolet light, and therefore they carry a lot of energy. When they are absorbed by some sort of tissue or cell, they deposit all of that energy into the tissue or cell and thus can either cause the various organic molecules that the cells need to work correctly to fall apart and not function anymore, or, and this is the part that's actually really scary, the molecules can be rearranged a little bit. And if you rearrange them in just the wrong way, those molecules actually survive and make copies of each other, which is what we call cancer. So if you have high enough doses of X-ray radiation interact with your body, you have a much higher chance of causing cancer in the tissues that those X-rays interact with. Hence, we try to limit our exposure to X-rays. Forms of electromagnetic radiation such as infrared light or radio waves lack the needed energy to penetrate deeply into most cells to cause this sort of damage, and so they're generally thought to be a good deal safer. Okay, so now that we've got the theory out of the way, let's take a little bit of time to look at the history of how these eyes came about. By the way, if you're feeling a bit unsure of all of this material, let me offer two things. First, we'll put up some links to a couple of Doppler effects simulations on the website at thescientificodyssey.typepad.com. One of the best of these can be found at the Nebraska Astronomy Applet Project, and it will let you drag both the observer and the source around, and you can see what the observer measures with respect to the waves sent out by the source, and you get a real good sense of how the Doppler effect thing works there. The other thing is to just remember that if the distance between the source and the observer is getting smaller, the frequency of the wave the observer sees will be larger. And the object's spectrum, if we're talking about light, will be blue shifted. If the distance is getting bigger, the observed frequency will be smaller. The object's spectrum will therefore be red shifted. So, who was the first person to think all of this up? Well, as you might have guessed, the first person to suggest the idea was a man by the name of Doppler, Christian Doppler to be exact. Doppler was a physicist at the University of Prague in Austria, at least at the time, and in 1842 he gave a lecture to the Royal Bohemian Scientific Society titled Concerning the Colored Light of Double Stars and Some Other Heavenly Bodies. He argued that, by analogy with both sound and water waves, just as we did in our theory part, that light waves should undergo a change in their frequency of oscillation if either the source of the waves or the observer were to move. Now, before we dig any deeper into this, we should make a comment about why this was a necessary thing to do. In 1842, when Doppler gave the paper, Young had shown that light was a wave, but no one knew what it was a wave in, what kind of wave it was, all sorts of things. While the understanding of the relationship between electricity and magnetism was getting better during this time, it would still be another 20 years before Maxwell would put all of the pieces together and show that electromagnetic waves were one of the consequences to a unification of these two natural phenomena. As such, no one knew if light was a transverse, longitudinal, or some other kind of wave. They also didn't know the medium through which it traveled. About all anyone really knew for certain is that it was a wave and that the physical property of the light that was determined by the frequency was the light's color. So, when Doppler writes and delivers his paper, he has to show that the effect works for all kinds of waves known, and then argue that if it occurs in those cases, it probably occurs for light as well. Now, the specific thing that Doppler is trying to argue is that double stars will have their color change depending on whether they're moving towards or away from an observer in their motions. Now, to be fair, this is actually a pretty good idea, and we discussed something like it in our last episode when talking about Pickering and Murray's work, first with Mizar and the handle of the Big Dipper, and then with Beta Aurigae. The problem with Doppler's idea is that he thought that the entire color of the star should change. In other words, if you had two white stars orbiting around each other, like in that skater example we used in our last episode, when one of the stars moved towards the observer, it would become bluer, and the other star moving away from the observer would become redder. And then they'd go white, and then the colors would reverse, and then they would go white again as the two stars circled each other like the skaters we talked about. Now, his model here has two really big flaws. First, he thought light was only being given off by stars in the visible part of the spectrum. I'm not sure why he would have thought this, given that there were already observations of both infrared and ultraviolet light in the spectrum of the sun by 1842, but that's why the stars would turn different colors. No light from outside the visible region would be shifted into what would be observed, and so for the star moving towards the observer, for example, the blue light would shift to violet, the green and yellow would shift to blue, the orange and red would shift to green and yellow, and so there would no longer be any reddish light to balance the other colors, and thus the star would look bluer. His other mistake was that he assumed that stars were moving through space at speeds that were significant fractions of the speed of light, something that would be necessary to get the amount of shifting that he thought was occurring. While his application turned out to be wrong, the fundamental premise was actually quite physically sound. The first empirical evidence for this was provided in 1845, when Christophorus Henricus Bias Below was able to demonstrate the principle for sound waves using wind instruments being played on a train. Which again, I think that's just the coolest idea. You know, you get these guys and they've got their flutes or their clarinets or whatever it happens to be, maybe it's an oboe, and they're sitting with their instruments hanging outside the windows of this train as the train goes by a stationary observer. Just a remarkably great thing. This, by the way, was confirmed by none other than our old friend Hermann Vogel when in I think it was 1875, he measured the pitch of a steam whistle on a train at rest and then when it moved towards and away from him. In the case of light, it was French physicist Armand Hippolyte Fizeau who demonstrated the effect at a meeting of the Société Philomatique in Paris in December of 1848. Fizeau was apparently completely unaware of Doppler's paper, and in his description, he correctly applied the principle not to the colors of objects, but to the shifts of spectral lines in either emission or absorption spectra. Given this much more correct application of the phenomena to physical systems, Fizeau's approach was more broadly accepted amongst his peers, even as it was not known outside of France until after 1870. There, the principle is actually known as the Doppler-Fizeau effect in honor of him. In 1860, Ernst Mach arrived at much the same conclusions, going so far as to show how line-of-sight velocities could be measured from stellar line shifts in the spectrum of a star. He wrote, quote, "The image of a star dispersed by a prism into a spectrum in which two kinds of dark lines are to be seen, one originating from our atmosphere, the other from the star. The latter must now, on a color change of the star, alter their position, and the velocity of the star is then determined from this shift." End quote. In other words, say you have an oxygen absorption line in the spectrum of a star. This line, it turns out, is not actually completely dark. While much of the light from that specific frequency of the rainbow spectrum coming from the surface of the star will be observed by the star's atmosphere, some of the light will still make it through. After traveling through space between the star and the Earth, that light will encounter the Earth's atmosphere, and more of it will be absorbed by the oxygen in the Earth's atmosphere, again at that same wavelength. Now, if the star is completely at rest with respect to the Earth, you'll only see one line, since both the stars and the Earth's atmosphere will absorb light at exactly the same frequency. However, if the star is moving with respect to the Earth, while the star's atmosphere, which isn't moving with respect to its surface, will absorb light at the same frequency, the light will be shifted a bit due to the fact that the entire spectrum will be shifted due to the star's motion with respect to the Earth. The light will then travel to the Earth, where the Earth's atmosphere will absorb the same frequency, but it's the same frequency in the Earth's reference frame. However, since the original absorption line will have Doppler shifted just a bit, as we said, there will now be two lines separated by a small amount. Measure this difference, Mach says, and you'll be able to calculate the velocity of the star. What's really remarkable is that these comments were made 2 years before the rebirth of trying to measure stellar spectra by men like Ferguson, Secchi, and Huggins. It's pretty amazing that both Fizeau and Mach were thinking along these lines when the idea of trying to examine stellar spectral lines was moldering in the back pages of one of Fraunhofer's technical journals, and men like Kirchhoff and Bunsen were still trying to figure out what was actually going on in the spectra of different objects. It would be Secchi and Huggins who would be the first to look for Doppler shifts in stellar spectra. The problem in doing this was that due to the really large value for the velocity of light, the size of the shifts would be very, very small. Given the technological limitations of the prisms and measuring instruments of the time, it would be pretty hard to reliably measure the shifts, especially given the fact that in the 1860s and early 1870s, all measurements were being made by eye. While Huggins would report having detected a Doppler shift for the star Sirius, it seems that the likely experimental error associated with his methodology was larger than the reported velocity measurement of about 20 kilometers per second away from the Earth. It wouldn't be until the mid-1880s that techniques and equipment would advance to the point where there was enough precision to make the needed measurements, and it wouldn't be Hermann Vogel who would be the one that would do it along with some others. The biggest advance prior to the use of photography was an optical system that actually created two spectra, one the mirror image of the other. This allowed the size of the shift to be doubled and thus much more easily measured. The other advance was the use of diffraction gratings in place of prisms. As you will recall, diffraction gratings create multiple spectral patterns. And thus, if you pick one of those spectral patterns that are many orders out, they'll give you much larger displacements for those higher order spectra, which make them more easy to measure. The place where these were first used were actually in measuring the rotational velocity of the sun. Here, instead of gathering light from the whole disk of the sun, the telescope would be pointed at what is known as the limb or edge of the disk, often using a slit in front of the objective lens to block out all of the other light. This light from that very small part of the sun was then dispersed either through a prism or by a diffraction grating, and the shift in the known Fraunhofer lines could be measured. In 1871, both Vogel and Secchi did this and arrived at rotational rates that were just a little bit higher than those determined by measuring the speeds at which sunspots traversed the disk of the sun as they were carried along by the sun's rotation. The values that Secchi and Vogel found were about 25 days per rotation around its axis at the sun's equator and 35 days near the pole of the sun. This meant that the surface of the sun did not rotate as a solid body, but rather that the equatorial regions would lap the polar regions once about every 100 days or so. And that turns out actually, when you want to talk about the sun and its magnetic field, something we may do down the road quite a little ways, that turns out to be a really important thing to understand. The only person here that seemed to be able to get pretty reliable estimates of stellar radial velocities, i.e. the speeds at which stars move towards or away from us, using visual measurement methods, was James Keeler at the University of California's Lick Observatory. As a side note here, the Lick Observatory was the first mountaintop observatory in the United States, having been constructed in the years between 1876 and 1887. Keeler not only used the 36-inch refractor there to make the best pre-photographic stellar velocity measurements, but he was also the first person to observe what is now known as the Inky Gap in Saturn's rings. His observation of those rings also provided the first empirical confirmation of James Clerk Maxwell's explanation that the rings were made up of many, many small bodies, each orbiting the central mass of the planet. Along with George Ellery Hale, Keeler also helped found the Astrophysical Journal, one of the world's preeminent publications on astronomical and astrophysical research. This, of course, was superseded by the advent of good photographic technologies to capture the details of spectra with increasing accuracy. This is where Vogel and his team at Potsdam would make their greatest contributions. By recording the stellar spectrum on a photographic plate in conjunction with the spectrum of a hydrogen light source mounted inside the telescope, Vogel could compare the known hydrogen lines with that of the star and then measure the shifts of the star's hydrogen lines, thus allowing him to determine the star's radial velocity. Now, at this point, I'd like to leave most of the historical advances aside, other than to mention that much of the really good work going forward would be done at the Pulkova Observatory in St. Petersburg and at the Lick Observatory and Yerkes Observatory in the United States, in addition to those advances being made in Potsdam. From here on, I'd like to focus on what can actually be figured out about a physical system from applications of the Doppler effect. And I say physical system because even though we'll be mostly talking about stars both here and down the road in our journey or narrative episodes, these techniques can be applied to just about anything, including nebula, planets, moons, and even rings of planets, as Keeler did when proving Maxwell's hypothesis. We've already talked about the first and most obvious thing a scientist can do: determine how fast something is traveling towards away or away from an observer. And again, like I said before, this is what astronomers call that radial velocity. This, when combined with the star's proper motion across the celestial sphere, gives a true picture of the star's actual relative velocity with respect to the sun. You got to do a little Pythagorean theorem calculation there, but it's pretty straightforward. By combining a bunch of these stellar velocities together, one can then determine the sun's motion through space and get a sense of how the sun is moving with respect to everything around it. One can also get a sense, as would be done in the middle of the 20th century, you can get a sense of galactic rotation from this by looking at high velocity stars that you can see from the Earth. The second thing, again as we've mentioned, is that one can image the disk of an object. Now, if you can do that, one can then determine the rotational rate of that disk by looking at light coming from one edge of the disk and then light from the other edge of the disk. This, of course, is most easily done with the sun, but it can also be done with planets that have atmospheres and with giant stars that modern telescopes can resolve into disks, such as Betelgeuse. This will lead us then to another application of the Doppler effect, though it's quite a good bit more difficult to untangle. As you might recall from our last episode, when Antonia Murray did her classification of stellar spectra, she noted that some stars had broad spectral lines with fuzzy edges, while other stars had lines with sharp edges, some of those lines being broader and some more narrow. While she didn't know what caused these differences, the idea had been put forward that if a star was rapidly rotating, a spectrum taken from the entire star would contain light from both limbs of the star, the one moving towards the Earth and the one moving away. This would cause the spectrum gathered to be both red and blue shifted, as light would be collected from parts of the star that were moving both away and towards the Earth. This line broadening, as it was called, wouldn't allow the rotational speed of the star to be determined if it could be properly characterized. While it would take some time to figure out how to model that, and also how to take data that was accurate enough to actually get the right amount of characterization, modern astronomers now use this technique rather regularly to determine the rotation rates of stars. Similarly, another cause of line broadening will come from the random motion of the gas molecules that absorb or emit the light in a spectrum. The faster they move, the more the line will be broadened. Since temperature is really just a measurement of the average speed of the molecules of the gas, the amount of line broadening due to this effect will allow for a determination of a system's temperature. Now, if you're like me and my students when I teach this in my astronomy classes, a question probably has occurred to you. How can an astronomer tell one type of line broadening effect from another? If both rotation and temperature cause a spectral line's shape or width to change, how can you tell the two apart? Well, it turns out that the way in which each physical process does this creates a line with different characteristic sorts of shapes. With a good bit of cleverness, it's possible to disentangle the two effects by modeling those combinations of shapes and thus get both pieces of information. It's a subtle and difficult piece of work to do, and it takes a good bit of skill and experience. And so that's one of the reasons that graduate students working in astrophysics had to take stellar spectroscopy classes for so long. Nowadays, though, with the advent of computer algorithms, we usually allow those things to assist in the process and thus allow for the most accurate determination of those values possible. At this point, I kind of feel like we've said everything we need to say about the Doppler effect, absent some specific application. As we continue forward in our narrative, we'll refer back to these ideas from time to time as necessary. However, if you've got questions or you feel like there's something I haven't talked about, shoot me a note. You can contact me at cldavies@mac.com and let me know, and I'll see if I can address that in a later episode. As we will see, the ability to use the Doppler effect to understand the motions of a number of deep space objects, as well as the ability to use spectral lines to uncover and understand the composition of those objects, will become a pair of powerful tools in the hands of a capable astrophysicist. As we wrap up, let me once again offer thanks to you all for listening to the show and participating in the voyage. This week's shout out goes to the folks in the St. Louis area who tune in. To Gary O'Brien and everyone else out there, it's great to have you aboard, and we'd love to see some pictures of you all on our Facebook page. So, if you get out to someplace, a science museum, the Arch, whatever, take a picture, post it out there, and we'll all give you a big round of applause. For all of you, if you have a chance and haven't already done so, won't you consider leaving us a strong review on whatever service you use to listen to the show? It helps us to spread the word by moving us up in the various rankings at all the sites that host podcasts. Apple Podcasts, Stitcher, iHeartRadio, Google Play, what have you. Also, if this is your first episode, you might find it useful to subscribe to the podcast so that you don't miss anything. I've got some pretty cool content in the works, and I want to make sure everyone gets a chance to enjoy it. Finally, a big thanks to the folks at the Blue Dot Sessions for the use of their compositions. They really are fantastic musicians, and what they produce is really quite remarkable. You can head over to their website at www.sessions.blue to hear more of their work. They've got all sorts of tools out there to help you find what you're looking for, so head on over and check it out. Next week, we'll spend some time getting to know more about the life and work of the women at the Harvard College Observatory. Until then, full sails on your journey.